myself. Hi, everyone. I want to thank first Coco Gomez and Colin Oriens, as well as the Hawk Cunningham lecture series for collaborating with Latin American Studies, which I hope is one of the first, is the beginning of a long relationship, really, of collaboration. As we study the planet's biosphere, there's been so much harm aggravated by climate change, and Latin America poses many problems as well as possible solutions. And so this idea of collaborating with environmental science in Latin America is wonderful for us, and I hope that the broader the dialogue, the better the solutions. So we're really excited to introduce Ines Camilloni, who is a professor from the Department of Atmospheric and Oceanic Studies of the University of Buenos Aires, where she's also the director of the master's program of environmental science. She's also a senior research scholar of the Argentina National Research Council called CONICET. And she is also affiliated to Harvard's Solar Engineering Research Program. She's been studying climate change since the 80s, and in addition to numerous articles and book chapters, YouTube postings, she has 2 books, one specifically on Argentina and climate change, and one more vast on air and water in our planet. Her approach analyzing and explaining what is happening is, I find particularly, is careful and nuanced and extremely clear for those of us like me who are not scientists, but are really concerned with what's happening and want to know more. And so I'm delighted to bring Ines here with us, and look forward to hearing what you have to say. Thank you.
Good afternoon. Thank you, Nina. Thanks for the invitation to participate with this lecture about climate change. I will share my screen so you can see the presentation. Oh, sorry. So this is the title of the presentation: Climate Change, Impacts and Solutions, a perspective from the Global South. As Nina mentioned, I'm a researcher at the University of Buenos Aires in Argentina. So to start talking about climate change, a good point is to stand where we are now related to climate change, and in particular to temperature changes. And this figure shows the evolution of the global average temperature related to the pre-industrial period, this 51 years between 1850 and 1900. And where you can see the blue colors, it means that global temperature was cooler than the average, and the yellow and orange and red colors means that the temperature was above the average. And as you can see, since at least half of mid-20th century, the anomalies of temperature, this means the departures from the average, were always higher than the average. This means that the planet is cooling, but not only that, but also the warmth of the planet is accelerating. If we consider the last year of this period, 2019, the departure from the pre-industrial period was above 1 degree Celsius, 1.1 degrees Celsius. And this number is good to keep it in mind for the discussion we will have in the following slides. But when we talk about global warming and climate change, it's important to know just not that the global temperature is increasing, but it's also important to note that the spatial distribution of the warming is is asymmetrical. This means that some regions of the world are warming faster than others. And this is what this map is showing. Here you can see that the Arctic is the region, the high latitudes of the Northern Hemisphere is the region where the temperature has been increasing more significantly. We have an increase of about 2.5 and 3 degrees Celsius, always relative to the pre-industrial period. And also, not only the air above continents is warming, but also the oceans are warming. But this warming is more important in the air above continents. And not only the average temperature is increasing, but we also have identified changes in extreme temperatures and in the occurrence, for example, in heat waves. And these two maps show trends in seasonal heat waves days and in the length of the longest heat wave for the period 1950-2014. And as you can see, this map is mostly yellow and red. This means that we have more heat wave days in the whole world, and these heat waves also tend to last longer. But in particular, this is more significant in the areas close to the equatorial latitudes and the tropical regions. And associated to this increase in temperature, we can also identify changes in the cryosphere. For example, these two images are from the Uppsala Glacier in southern Argentina, in the southern Andes. One is from 1931, the other one is from 2016. And you can see how impressive is the melting, the ice melting in this glacier. But this retreat in this glacier is not only measured, or you can find it also in other glaciers in the southern Andes. For example, this graph shows this trend in the balance, these negative trends in the balance of water in the southern Andes. And this slide shows the increase in the global average, sorry, there's a mistake there, in the sea level for a short period, but because this information comes from satellites. And we can see also that there is an increase in the sea level. And there are the two different factors associated to this sea level change. One of them is related to the added water from melting ice sheets and also glaciers. And the other factor is associated to the expansion of the water as it warms. As I showed before, oceans are also warming. And for the last decade, these two factors are both important to explain this increase in the sea level. But during the last 10 years approximately, the added water from the melting ice sheets have become as the most important cause for this sea level rise. And also we identify changes in the rainfall, in the distribution of rainfall. We have some regions where we can identify an increase in precipitation, the green areas you can see in this map. And we also have some other regions where we have a reduction in precipitation. And these changes are different than what we have identified in the cases of temperature, where we have a general warming of the planet. And for example, in South America, we identify some regions with an increase. And in particular, in Southeastern South America, this green area you can see here in the map is in particular one of the regions where the increase in precipitation has been more significant. And on the other side, for example, in the Amazon region, we have some areas with a significant reduction in precipitation. These changes in the distribution of water has significant impacts in different ecosystems and also in water availability, in particular for this region. But in general, what we can say is that changes in precipitation show that we have more water available in those regions that they are already very humid regions. And we have a reduction in precipitation in those areas that they are already very dry. And in the jargon of the climate change community, this is interpreted in some way that rich people are becoming richer in terms of fresh water availability, while poor people are becoming poorer, or always in terms of this fresh water availability. So if we can summarize some of the things we know about climate change in general, we have seen that temperature is increasing with different patterns above when we consider continents and the oceans, and when even the distribution of this warming within the continental areas is quite different. But we also have an increase in extreme events, in particular heat waves, that they tend to be more frequent and to last longer. We also identified changes in the ice sheets and in glaciers. They are melting all over the world, and in particular in South America, in the southern Andes, this situation is quite critical. Also, sea level is changes. We have sea level rise identified for the last 100 years. And precipitation is also changes with this particular pattern of increases in some regions and decrease in other regions. And also extreme events are changes producing droughts in some areas of the planet and floods in other regions. So this is what has been happening. And the next question is, why is climate changing? Which are the causes of these changes? And in particular, what we know is that human activities are the most important factors associated to climate change, at least to explain the changes I mentioned before for the last 60 or 70 years. In first place, we have the burn of fossil fuels as one of these human activities responsible of emission of greenhouse gases to the atmosphere that intensify this phenomenon. Also, land use changes. For example, in the case of deforestation, when we replace the land cover for agricultural activities, for example, these changes introduces modifications in the climate system that produce climate change in many variables of the climate, but also the expansion of the urban areas produce climate changes too. The replacement of the natural cover of areas for buildings or streets or different urban materials, they all produce or they all introduce changes in the atmosphere. Also, some activities as agriculture and livestock farming, they also introduce different gases into the atmosphere, greenhouse gases into the atmosphere that produce climate change. And also we can add to this the production of solid waste, mainly. They also contribute to the modification of the atmosphere, the chemical modification of the atmosphere, also introducing greenhouse gases. And this is the distribution of the greenhouse gases that are incorporated into the atmosphere as a result of these human activities. And more than 70% of these injection of greenhouse gases are from anthropogenic activities are related to CO2, carbon dioxide, and in the other greenhouse gases are that we are incorporating with these human activities are in much less proportion. This is why we always tend to talk about CO2 as related to climate change, because it's the greenhouse gas that is incorporated with mostly into the atmosphere. And this is the evolution of the atmospheric concentration for a long time, since many years ago. And you can see that never before we have at least the values, the concentration we have of CO2 in the atmosphere that we have in average in last year, about 400, but that this increase in the concentration of CO2 was quite critical and exponential since the Industrial Revolution. And when we look the concentration of CO2 in the atmosphere, this is the CO2 that is measured in Mauna Loa, in Hawaii. These measures start in the 1950s. What we can see is the concentration is increasing, and this graph is quite important because it shows that although we know that climate is changing and the forcings of these changes are related to human activities, fossil fuel burns, and also some land use changes and all the activities I mentioned before. This curve showing the increase of CO2 in the atmosphere is not changing. It's still increasing in a very significant way. And when we want to understand in some sense responsibilities of these emissions of CO2 into the atmosphere, we can analyze this graph that shows cumulative CO2 emissions from activities in different countries. And what we can see is that the first emitter is the United States. Sorry, my dog is barking. And in second place, we have an emerging country, and this is China. So we have as the biggest emitters two countries, one a developed country and the other one is a developing country. And this is important to keep it in mind, because although these two countries are the most important contributors to CO2 in the atmosphere, there's something that they have different. And in this sense, what we can see is that the moment when the United States start to emit or to introduce CO2 into the atmosphere was in the 19th century, while in the case of China, this was by the mid of the 20th century. in this graph, you also have some countries from Europe, Germany, and United Kingdom, and they also start their emissions at the same time, mostly as the United States. And also we have other emerging countries as India or Argentina. We have much lower emissions here from Argentina, and we also start incorporating CO2 into the atmosphere mostly during the 20th century. So it's important to keep in mind, as I mentioned before, that climate change is a universal problem, and all countries must address this problem. But we also must consider the individual capabilities of the different countries and also their historical responsibilities in order to guide the efforts to limit the emissions of greenhouse gases into the atmosphere. This is why we talk about this common but different in responsibilities among the countries when we compare developed countries and emerging countries. So why we should all care about climate change? And we should all care because climate change produces impacts and also risk. We talk about impacts when we want to explore and analyze what has been happening related to climate change. For example, what I showed before, how much the sea level has risen, or for example, how much the discharge of a river has changed. So impacts is related to something in the past, something that has happened and that we can measure. And risk are, when we talk about risk, what we want to express is something that may happen, something that is in some way associated to a probability of a possible impact, but something that has not happened yet. So risk is, when we talk about risk, we are talking about the future. And when we talk about impacts, we are talking about the past. But in both cases, we have identified impacts and risks associated, for example, to the water availability and also water quality because of this change in precipitation patterns, and also changes or impacts and risks associated to health because of diseases that can be transmitted by mosquitoes, for example, and we talk about malaria and dengue and Zika and different diseases, and also risks and impacts on biodiversity. We have identified that many species are on risk of extinction, and this could increase in the future. Also, changes mostly in extreme events, in extremes of temperature, but also on precipitation, produce migrants, what we call now climate refugees or climate migrants, because they have to move from their own home to some other places where they can find more better environmental conditions. And these also have some economic impacts and risks associated to all these modifications. And also there's some impacts and risks associated to food security, because we have the global population is increasing, and in some regions the capacity of producing food is not enough to feed the population that they already have and they are projected to have in the coming years. So this is why we care so much about climate change, because of these impacts and risks. So the question is, if we can solve climate change, is there some way to solve this problem? And we now tend to talk just not as a problem of climate change, but as a crisis related to climate. And in this sense, in 1994, entered into force this environmental treaty in the United Nations Framework Convention on Climate Change, where the objective of this convention is to stabilize the emissions of greenhouse gases into the atmosphere, to prevent dangerous interference with the climate system. And this convention has up to now 197 signatory parties. We talk about parties and not countries, because as part of this United Nations Convention, we have not only single countries, but also some group of countries, for example, as the European Union. And this convention has annually meetings in some city in the world. These meetings are called the Conference of the Parties, where they discuss different issues related to climate change. And the most famous of these Conference of the Parties was the one held in Paris in December 2015, where it was signed the Paris Agreement that entered into force 1 year later in 2016. And the main goals of this agreement are related to hold the increase in global temperature to values well below 2 degrees Celsius above pre-industrial levels, and to ensure the efforts to limit this temperature increase to 1.5 degrees Celsius. And this more ambitious target of 1.5 degrees Celsius was mostly wanted for by the less developed countries, and these countries, those countries that are really in danger because of sea level rise. And to address this goal, all of the parties that are part of this agreement has to present what it is called their national determined contributions, where they express in which way they will reduce their emissions of CO2 and the other greenhouse gases into the atmosphere, just to address these warming levels targets. And this is the status of the Paris Agreement, the current status. As I mentioned, we have 197 parties participating in this agreement. 188, they have already signed the agreement, and they also ratified the agreement. We have just 7 countries that, although they signed, they have not already ratified it. And as you may know, we have just 1 country that has withdrawn of this Paris Agreement, although we hope that they will go back soon to this Paris Agreement, because all the countries that they have already signed, if we sum the amount of greenhouse gases emissions, they are close to the 80% of the total of the greenhouse gases emissions. But United States is responsible for close to the 18% of the greenhouse gases. So when we explore where we are now related to the Paris Agreement, these are the two targets we have, the most ambitious target and the general target, the 2 degrees target to limit the global warming compared to the pre-industrial period. And if we consider the NDCs that were presented by many of the countries, most of the countries that are part of this agreement, if we consider that and the reductions in the greenhouse gases emissions they are proposing to do in the following years, by the end of this century, the increase in global temperature will be about 3 degrees warming. But at least this is better if we continue in this current pathway, in the current pathway of emissions we have that will take us to a world of 4 degrees warming above the pre-industrial period. But we are in any way considering the NDCs or considering the current pathway, we are quite far from the warming targets of the Paris Agreement. So this is what I used to say, that we are in an inaction pathway that will take us to this 4 degrees warming world, where the average is 4 degrees, but this will mean that in some regions temperature will increase much more than 4 degrees, more than 10 degrees in the Arctic, for example, and the temperature increase will be also higher in the continental areas where we all live, and also the oceans will be warmer and warmer, and the combination of this situation will produce, for example, an increase in the cryosphere melting, and sea level will continue rising. So we are in this pathway. This figure shows the change in global temperature relative to the pre-industrial, and everything up to now, it seems that we are now in 1.1 degrees above pre-industrial, and that if we continue, as I mentioned before, emitting CO2 and the other greenhouse gases as we are doing now, we will reach quite soon 1.5 degrees, and temperature will continue increasing during the following years. So this is in opposite to an action, climate action, that if we reach the most ambitious target of the Paris Agreement, 1.5 degrees global warming, this is also, and again, an average. We will have some areas of the world that where the temperature increase will be much more than 1.5. And in any way, although this is the most ambitious target of the Paris Agreement, it means a warmer world compared to the today world. So what we can expect to have in this 1.5 world is more extreme weather events, and sea level rise will continue rising, the cryosphere will continue melting, and we will have the same, or we will find important impacts on the different natural systems and also human systems, as I mentioned before. But this is important to keep it in mind, that the 1.5 degrees world is better than the world where we are living now. So this action means that the best situation we can have is that we can stabilize the global warming in 1.5 during the rest of the century, to limiting the greenhouse gases emissions, and also removing CO2 from the atmosphere just to keep temperature lower than 1.5 degrees. And to do this, the annual reduction in CO2 emissions between this year and 2030 has to be around 70% each year. It's a quite important reduction we have to accomplish each year just to reach the most ambitious warming level target of the Paris Agreement. And another possible situation is that we cannot limit the increase in temperature in 1.5, and we have some kind of overshoot of temperature for some time. We don't know for how long this could happen, but for some time, temperature during this overshoot it will be higher than 1.5. It can be 2 degrees, we don't know, but this is a possible scenario for the next year, just for some time exceeding this ambitious target of the Paris Agreement. So the question is, for how long this could happen, to have this overshoot, for how much? And in case we have this overshoot, what can we do to cool the planet? How can we, what can we do to reduce temperature just to finally reach this 1.5 degrees and keep temperature in this value? And here is where climate engineering comes in the discussion as a possible way to reach this 1.5 degrees target. And how can we define climate engineering? Is an intentional large-scale intervention in the Earth's climate system just to counter the human climate change. We want to, in a deliberate way, to modify the climate just to cool the planet in a very quick way. And how can we do that? We have different options. One of these options is related to CO2 removal, and we can do that by means of afforestation and reforestation. This means that because of the tree growth, we can take CO2 from the atmosphere. But we can also have some other ways to remove CO2 from the atmosphere, and this is considering producing energy, bioenergy from the plants, burning the biomass, and then to capture and storage the CO2 in not sending back the CO2 to the atmosphere, but just to not releasing the CO2, but just capturing it and storing the CO2 underground when the CO2 has to be there for centuries. And the other way to cool the planet with this climate intervention is associated to the modification of the solar radiation, just to produce an effect to reflect more solar radiation than what we are doing now. And this is other way to cool the planet. And in this sense, we have two possibilities to manipulate the solar radiation. One is called the stratospheric aerosol injection, that we want to do with this technology is just to replicate the effect of volcanoes, injecting into the atmosphere some very small particles that we call aerosols, that these aerosols will contribute to reflect much more solar radiation than what we are doing now. And the other way is to produce this solar radiation modification is to make clouds, marine clouds, brighter, using also some kind of aerosols, these small particles that will help to enhance the reflectivity of solar radiation. But these two techniques that we also call climate engineering or geoengineering, they are unconventional technical options, and we cannot avoid, when we present this kind of technologies, the discussions on the possible impacts they can produce on ethics, because with implementing these kind of technologies, we will still making changes in, and we don't really know all consequences of these changes. And also we need to discuss the international governance of this kind of technologies if we want to make changes in the global climate. Who will decide if we are going to implement this kind of technologies, for example? Who will pay for the implementation of these technologies too? And for example, in the case of CO2 removal, we are, one of the questions is related if this could make some land use competition. We have to produce food. As I mentioned, we have a significant population increase, and is projected to increase in the following years. So if we need this land to produce this CO2 removal, can we be sure that we will produce enough food for everybody? And related to the solar radiation modification, we are not sure yet about the possible side effects that this kind of technology could have. And in this sense, I'm conducting a study project just to assess the hydrological impacts of solar radiation management in La Plata Basin in South America. We want to know which climate risk would change, and this means could be avoided, reduced, or even could make worse in La Plata Basin if stratospheric aerosol injected is implemented. We know that, for example, Argentina is not a country that will have the technology to implement this kind of technology, but we want to know the possible impacts we may have if this is implemented by other countries in the world. And these are some of the results of this project. These are temperature changes when we compare the implementation of solar radiation management with a high emission scenario. This scenario is called RCP 8.5 for maximum and minimum temperature. In both cases, what we can expect is with a cooling effect associated with this solar radiation modification. This is what we expect to happen if we can reduce the amount of solar energy we are receiving. La Plata, this is South America, and this line, this contour, shows La Plata Basin in southeastern South America, and this basin is shared by Argentina, Brazil, Uruguay, Paraguay, and Bolivia, by 5 countries in South America. And this result associated to a cooling effect is what we expected, but we also found that if somebody implements this solar radiation modification, we can expect changes in precipitation in our region, with some regions where precipitation will increase. These are the green areas, and some regions, the brown areas, are those parts where precipitation will reduce. And this will have impacts on flows of the main rivers in this basin. And for example, at this location where we have this large dam, this dam is shared by Paraguay and Brazil. The name is Itaipu Dam in the Paraná River. We wanted to know if we can expect changes in the flows in the Paraná River, because this dam is quite important for these countries because it produces hydroelectricity. And what we found is that for the next 30 years and for the for mid-century, what we can expect is an increase in the mean flows of the Paraná River, at least at this point, Itaipu. And this could be, this increase in the mean flows can be interpreted as a positive result because it could mean more water to produce more energy. And in terms of extreme flows in minimum and maximum flows, we have, for example, that for minimum flows, the implementation of the solar radiation modification will produce an increase in the mean flows. And this is the same that what we found for the maximum flows. So in one case, the increase in the minimum flows also can be interpreted as a positive result because we cannot expect some significant droughts, for example, as the one we are having for the last months in the Paraná River. So flows will be not so low as they are now. But in the case of the maximum flows, we can expect, for example, an increase in the frequency of floods in the margins of this river. So to conclude with this presentation, and mostly related to this technology of solar radiation modification, is important to know that this is not an alternative to mitigation and adaptation to climate change. Mitigation is how we reduce the emissions of greenhouse gases, and adaptation is how, in which way we can adopt different measures just to protect the different systems against the negative impacts and risks associated to climate change. But what we know related to this technology is that it's the only way, at least the only quickly way to stop or to slow the rise in global temperature. And the climate simulations, those simulations that we use to produce these scenarios of changes in the flows of the Paraná River, we use climate models, also a hydrologic model, show that in some regions we have some information, but still this information is limited. We need more research because we have large uncertainties about related to the possible impacts of solar radiation modification. And also this discussion about these climate interventions also have some social and political aspects that are really complex, and they also need to be discussed. And just to finish this presentation, related to this, to keep in this deliberate way the intervention of climate, the question is, we want to cool the climate, but who decides how much we have to cool the planet? We want to go back to the pre-industrial period. We want to go back to the 1950s, for example. Who decides that? And I think this cartoon shows this discussion we have about these climate technologies in a very good way. So thank you very much. And this is the end of this presentation.
Thank you very much, Ines, for a great overview, and also for introducing a technology that I don't think we have ever had covered in this series. So it's always nice to learn something new. So I have a question and a comment while people collect their thoughts. And just so you know, audience, you can raise your hand and say your question out loud, or you can write it in the Q&A. So first, my comment for those of you in the audience who are interested in these international negotiations. Ines mentioned the COP conference. And for those of you who don't know, I wanted to say that TAPS actually sponsors a group of faculty, students, staff from our university to go there every year. And this is sponsored through the Tufts Institute of the Environment. And I want to put the link here in case any of you is interested in experience these negotiations, you can apply to it. And let me see, let me put the link. There we go. And then my question is, so clearly solar engineering is still far away, maybe more in terms of ethics and social aspects than the actual technology, but I wanted to know about the technology side. So what, how far is the field in terms of how close are we to actually be able to do this physically? What kind of evidence do we have that this would work at large scales?
The evidence we have is related to simulations. We can simulate the climate using global climate models, and we know the effects of volcanoes eruptions, and we can reproduce that in the climate models. And what we know is when we have this kind of eruptions, an important eruption, and some aerosols go into the stratosphere, there's a cooling effect. So with the climate models, we can reproduce this kind of cooling effect. The situation is that when we have a volcanic eruption, we are introducing into the stratosphere sulfates, and we cannot do the same in the case of solar radiation modification, but because we know that sulfates are bad for stratospheric ozone, and we don't want to harm the ozone we have in the stratosphere. So the idea is to the solar engineering group of Harvard, they are preparing a field experiment because there are some measures they want to do, and the only way to do that is into the atmosphere. You cannot reproduce the stratosphere environment in a lab. And what they are planning, the name of the experiment is COPEX. You can look for this experiment in the web. And they are planning to release a balloon into the atmosphere with some substances. And they want to release, I think, a kilogram of this substance and make some measurements to explore the chemical reactions into the stratosphere. And this is one of the experiments they are planning. I think the plan was to do this experiment this year, but because of this, the pandemic, it was probably postponed. I don't know for when. And this is one of the ways they are working to explore that. But in case we really want to implement this kind of technology, we will not use, I'm saying we, not me, but balloons are not going to be used for that. We need planes to release large amounts of this kind of aerosols. What I know is that we don't have this kind of planes yet that they can fly into the stratosphere, but they are working in the design of these planes. And this technology is not very expensive. So when we have all this technology prepared, I don't know, in 5-10 years, as it is not very expensive, the idea of the implementation of this is not so science fiction, I would say.
Thank you. Let me see. It looks like there is a question. So, Colin, do you want to just say it out loud?
Sure. I thought you talk about the implementation not being very science fiction, which I think I totally agree with you. You also made a note that Argentina doesn't have the technology to make a decision and to implement it on its own. And so there's been a lot of discussions about who decides and who has a voice at the table. So my question is, what process or system would you like to see in place from the Global South perspective to ensure that all voices or specific voices are being heard as the idea of implementation might be put into place?
But I think that the first thing is to have the research from the Global South of the possible impacts of this technology. And this is why I'm conducting this project, but there are other 7 groups that from the Global South. The name of this project is Decimals. We are all working on the possible impacts of solar radiation modification in our regions. Because what we thought that this is the first way to have a voice in the discussions about governance of this kind of technologies, just to at least inform decision makers from our countries about the possible impacts and if it could be good or bad or what which is the best position for our countries in the discussion. What we don't know if the discussions will be in the United Nations Convention or of framework or in other kind of institution to this kind of things. Nobody knows yet how this can be discussed. But what we really know is that the Global South will not have the technologies and the money to produce this kind of changes in climate. But what we really know that we will see the impacts. So we want to know in advance which this impact could be.
Well, thank you very much. And let's all send a clap for Ines. Virtual applause. And if you have questions, I'm sure you can connect with Ines offline. So thank you very much, and we will see you next week.
Thank you.
Gracias.